This is Physics 2120, Lecture 14, and today we're going to talk about sources of the magnetic field. In particular, we're going to introduce something called the Biot-Savart law. So Biot and Savart conducted experiments on the force exerted by an electric current on a nearby magnet, and they arrived at a mathematical expression that gives the magnetic field at some point in space due to a current. So let's look at our situation. Let's say I have some sort of current flowing in a wire, and I want to know what the magnetic field is out at some point in space. Well, a little bit of magnetic field created by a little bit of this current we'll call dB. The length element is ds. And of course, this wire is carrying a steady current of I. The vector dP is perpendicular to both ds and the unit vector r hat, where r hat is a vector that's directed from the current element pointed to the place where we want to know what the field is, P. And the magnitude of dB is inversely proportional to r squared, where r is the distance from the current element to P, the place we want to know the magnetic field. The magnitude of dB is also proportional to the current and to the magnitude of the length element ds. And the magnitude dB was also found to be proportional to sine theta, where theta was the angle between the vectors ds and r. So all of those observations are summarized by a mathematical equation that we call the Biot-Savart law. dB is equal to mu naught over 4 pi times I ds cross r hat in the r direction. So the magnetic field described by the law is the field due to current carrying conductors. Now mu naught is a constant. It's called the permeability of free space, and it's just 4 pi times 10 to the minus 7 Tesla meters per amp. dB is the field created by the current in this length segment ds. So if I want to find the total field at any point, I need to add up the contributions from all current elements. So I need to integrate, and so B becomes mu naught I over 4 pi times the integral of ds over r hat in the r over r squared. And this integral is over the entire current distribution. Now this integral looks very complicated, and it can be, but we're going to break it up into parts. We're going to look at direction separately from magnitude and see if we can't get a hold on how to use this equation in a more simple method. So this law is valid for current flowing through space, not just current flowing through a wire. ds represents the length of a small segment of space through which the charges flow. For example, in an older style television set where we had a cathode ray tube or a CRT, we had an electron beam flowing through space. Well, there was no wire, we just shot electrons at the phosphorus screen. Those moving charges still create a magnetic field. Now, let's compare magnetic field to electric field. First thing, let's compare distance. The magnitude of the magnetic field varies as the inverse square of the distance from the source. That was similar to the electric field because it was also varied as the inverse square of the distance from the charge. When we look at direction, the electric field created by a point charge is radial in direction, whereas the magnetic field created by a current element is perpendicular to both the current element and the unit vector r hat we talked about. If we look at the sources, electric field are established from an isolated electric charge. For a magnetic field, a current element that produces a magnetic field has to be part of an extended current distribution. So we have to integrate over the entire current distribution. I can't have just a single piece of current. And if we look at magnetic field lines, they have no beginning and no end. They always form continuous circles. whereas electric field lines began on positive charges and ended on negative charges. So, the best way to understand Biot-Savart is to look at some examples. And so let's work through some examples and see if we can see how this is being used. Let's start by looking at the magnetic field from a long, straight conductor. So say I have a thin, straight wire that's carrying a constant current I. What is the field up here at point P? In this case, the magnitude of ds is just going to be dx. We're going to put our wire along the x-axis. We know dB is mu naught I over 4 pi ds cross r hat over r squared. So, the first thing we're going to do is look at direction. So, ds cross r hat. Well, ds is in the x direction, and r hat here, it's going to have an x component and a y component. So to figure out r hat, we look at the length of this distance r divided by its magnitude. So this vector r here is x in the x direction plus a in the y direction divided by its magnitude gives us r hat. Now remember, x hat cross x hat is going to be 0, and x hat cross y hat is equal to z. So the direction of the magnetic field at this point here is in the z direction, which using our right-hand rule we see is straight out of the page. Now that we have the direction, we can look at the magnitude of ds cross r hat. So it's dx, and then it's a over the square root of a squared, x squared plus a squared, or it's dx sine theta. So the magnitude dB is mu naught I over 4 pi dx sine theta over r squared. To get the total magnetic field, then we need to integrate. Mu naught I over 4 pi is constant, it comes out, and so need to integrate dx sine theta over r squared along the current. Now, we can see from the picture that dx and theta and r are all related. As one changes, the other changes. So we need to find some relationships between all three variables. We know that x is equal to r cosine theta. So dx would be r sine theta d theta. However, we don't want to use those variables because integrating over theta is going to be difficult. What about a equals r sine theta? Now, that's got problems also, so we try another one. Well, let's see, tangent theta is a over minus x. So then x would be a cotangent theta, and then dx would be a cosecant squared theta d theta. Now, in this case, I have everything in terms of theta, whereas before I had dx in terms of r's and thetas. I didn't want that. And here's a relationship between r and theta, but I needed x. This one, though, gives me everything I want for dx in terms of just theta. However, from this one, I can also get r as a function of theta. R is equal to a cosecant theta. So now, I can plug these in above and see what b is equal to mu naught I over 4 pi. Dx was a cosecant squared theta d theta times sine theta, and r was a cosecant theta, and we square that. We'll see the cosecants go away. And so I end up with just mu naught I over 4 pi. I'm going to have an extra a on the bottom here. It comes down. I integrate sine theta d theta. This is an integral that we can do. The integral of sine is minus cosine. And I plug in my limits from theta 1 to theta 2. And there we have it. B is equal to mu naught I over 4 pi a times cosine theta 1 minus cosine theta 2, where theta 1 would be this value when we start at this place, and when we get over here, theta 2 would look something like this. So, if this conductor then was an infinitely long straight wire, then out at infinity theta 1 goes to 0 and theta 2 goes to pi. So if that's the case, then cosine theta 1 is 1 and cosine of pi is minus 1. So I get mu naught I over 2 pi a. Looks like we got some variable problems here. Mu naught I over 2 pi a. Now this is an important result, and we're going to come back to it again later. So if I look at this magnetic field from the long straight wire, we figured out its magnitude, mu naught I over 2 pi a. And in our picture we said it was coming straight out. It was perpendicular. No matter how we turn it, it would always be coming straight out from above. So the only way that can work is if the magnetic field makes circles around the current. So the field lines are concentric with the wire. They lie perpendicular to the line planes perpendicular to the wire. The magnitude of the magnetic field is constant on any circle of radius A. And we can use the right-hand rule to determine which direction. If we put our thumb in the direction of the current, our fingers will curl around the direction of the magnetic field. Now what about a curved wire segment? Let's find the magnetic field here at O due to this wire segment. So we have current coming in radially inward, then goes around this curved wire segment, and then radially outward. Here, theta will be measured in radians. So let's find the field at point O due to the wire segment. I and R are constants. So dB is equal to mu naught I over 4 pi ds cross r hat over r squared again. Well, first, if we look at the segments coming in radially, we notice that ds and r are parallel to each other, so the cross product gives 0. So from A prime to A and C to C prime, I'm going to get no contribution to the magnetic field at O. So the only part is the curved line segment. And so ds along the curved side line segment is already theta, and it's in the minus theta direction. And r hat is, of course, just r hat, and theta cross r hat is the z direction, if we use cylindrical coordinates. So the direction is minus z, where the direction is into the page, everywhere along the curved wire. So now that we know the direction, we can just look at the magnitude. So ds cross r hat is just going to be ds. They're perpendicular to each other already, so the sine of that angle goes to 1. And ds along the line segment is just r d theta. So integrating the Biot-Savart law, I get b is equal to mu naught I over 4 pi times the integral of ds, which was r d theta, over r squared. Now r is a constant, so the 1 over r comes out. And I just end up integrating d theta from 0 to whatever angle. So the magnetic field is mu naught I over 4 pi r times theta. Now I can continue this and consider a magnetic field at the center of a circular loop where theta just goes to 2 pi. And if that's the case, then when I plug in 2 pi for theta, I get that the magnetic field at the center of a circle due to a current in it is mu naught I over 2r. What about a point off the axis of a loop? So let's use Biot-Savart to figure out the magnetic field at this point due to this current going around this loop. Say the loop has a radius r and a steady current I. First, we start out again. What is the direction? Well, we know that the direction at this point is ds cross r hat. So if I were to use my right hand rule and go ds cross r hat, and r hat is pointing down at this angle, I use my right hand rule and I see that dB points up in this direction. Now, as I integrate around here, and if I look at a part down here, the magnetic field from this would be off in this direction. And I could, again, figure out its components. There would be a component here and a component here. So the components in the y direction, or up and down, or in the z direction for that matter, all cancel out due to symmetry. So only the x component survives. So we know that the magnetic field at that point has only an x component. So now that we know the direction, we just need to figure out the magnitude. So first, ds cross r hat, in this case, again, is just ds, which is r d theta around the loop. Now, over here, we see that the x component is going to be dB cosine theta. So dBx, the little bit of the x component, is mu naught I over 4 pi ds cross r hat over r squared times cosine theta. We know that r here is capital R squared plus x squared, the distance out. And cosine theta is big R over little r, which is big R over the square root of x squared plus r squared. So now we can plug this all in. Bx is mu naught I over 4 pi times the integral of ds over r squared, which we said was x squared plus r squared. Cosine theta, which is r over the square root of x squared plus r squared. And we pull out all of our constants. On the bottom, we get the x squared plus r squared now to the 3/2 power, and we get an r on top, and we're integrating ds. Well, as we integrate ds around a circle, we just get the circumference, which is 2 pi r. We can see that because ds is r d theta, and the r will come out, so it becomes r squared. Integrate d theta, I get 2 pi. And so the magnetic field at this point, due to the current, is mu naught I r squared over 2 times x squared plus r squared to the 3/2 power. Now consider the field at the center of the current loop. At that special point, x equals 0. So we plug in 0, we get that the magnetic field is mu naught I over 2r. That's exactly the same result as we got from the curved wire. Now let's look at some magnetic field lines for this loop, exactly what they look like, because we figured out what it was at the center and along that axis, but not necessarily all of them. Well, we know that magnetic field lines make concentric circles around a long straight wire, and it kind of does the same thing for a current loop. Figuring out the field off axis, as it's called, is a rather difficult problem, and it's outside the scope of this course. But this is what it's going to look like. And you can certainly see this if I have a current loop here with some iron filings. You can kind of notice that here, the iron filings. It looks rather similar to the magnetic field lines of a permanent magnet. Now the next thing I want to look at is the magnetic force between two parallel conductors. So let's say I have two parallel wires and they're each carrying a steady current. Well, the field B2, due to the current in wire 2 that exerts a force on wire 1, the force on 1 is ILB, where B is the field from 2. And B2 we know is given by this formula. So we put those together and we get that the force is equal to mu naught I1 I2 over 2 pi a times the length. So parallel conductors carrying currents in the same direction attract each other, and parallel conductors carrying currents in opposite directions repel each other. The result is often expressed as the magnetic force between two wires, FB. It can also be given as the force per unit length, or F over L is mu naught I1 I2 over 2 pi a. So this allows us to define what an ampere is. The force between two parallel wires is used to define the ampere when the magnitude of the force per unit length between two long parallel wires that carry identical currents and are separated by 1 meter is 2 times 10 to the minus 7 newtons per meter. The current in each wire is defined to be 1 amp. And that allows us to define the coulomb. The SI unit of charge, the coulomb, is defined in terms of the ampere. When a conductor carries a current of 1 amp, the quantity of charge that flows through a cross-section of the conductor in 1 second is 1 coulomb. Now, going back to the magnetic field of a wire, we can also use a compass to detect what that magnetic field is and to test what we derived mathematically is true physically. When there's no current in the wire, there's no field due to the current, and then all the compasses would line up with the Earth's north pole due to the Earth's magnetic field. As I turn current on in the wire, the compass needles will deflect, and they will form a circle around the wire. And this shows the direction of the wire produced by the magnetic field, which is exactly what we said it should be using our right-hand rule. In fact, we can see this experimentally if I have a wire and I have a high current going through it and I have iron filings on a page perpendicular to this wire. We see that the iron filings all line up in concentric circles. So, we can review what we talked about today. We started with the Biot-Savart law. dB is equal to mu naught I over 4 pi ds cross r hat over r squared. And that we can use this to integrate to find the magnetic field due to any current element. And we looked at fields from currents. There's form circles around the current, and the direction is always determined by the right-hand rule.